So we're happy to have Nikos Frantzikinakis today speaking about ergodic properties of the Liouville function and applications.
Okay, so first of all, thank you very much to the organizers for giving me the opportunity to speak on this very nice series of seminars. So whatever I will say today is joint work with Bernard Host, and our goal is to study statistical properties of multiplicative functions, and I will focus on the Liouville function using techniques from ergodic theory. Okay, so I will start by introducing the main players. So the first thing is just some notation on averages, and we're going to discuss statistical properties of the Mobius function and later of the Liouville function. The Mobius function is defined to be -1 to the k when n is a product of k distinct primes, and 0 if it's if n is divisible by a square. Okay, so the Mobius function is considered the queen of multiplicative functions. It appears on several identities in elementary number theory, and it is also linked with distributional properties of the prime number. Okay, the reason is that there is an identity connecting the von Mangold function, which is basically the indicator function of the primes, appropriately weighted so that the average is 1. So this elementary identity that follows from the unique factorization theorem connects the von Mangold function with the Mobius function. So in particular, if one would like to get asymptotics for correlations of the von Mangold function, from which you will get asymptotics for expressions about the primes, it suffices to prove estimates for the Mobius function. Now the Mobius function is ±1. The values that are ±1 are supposed to be randomly distributed, so we expect all these correlations, at least when the nj's are distinct, to converge to 0. But okay, if you want to prove things for the von Mangold function, not only you need to prove that these things go to 0, but that they go to 0 with some appropriate speed. And the speed that works is logarithmic saving with some power that depends on the number of sheets. And also a similar statement you would like to prove for arithmetic progressions. I'm just simplifying life a little bit. So I'm not going to tell you anything about estimates of this strong form. So we look on problems of intermediate difficulty. We just try to see when these averages go to 0. Okay, so nothing that I will say will have any impact about averages of this form. Okay, but okay, first things first. Okay, so for practical reasons, I will focus on the very close relative of the Mobius function, which is the Liouville function. Okay, one slight advantage is that it is completely multiplicative. The Mobius is just multiplicative, but for me, it's an advantage in terms of terminology. Various problems that I will phrase are just simpler to phrase for the Liouville function, but whatever I will say is easily transferable to the Mobius function, or if you had something about the Mobius, it's easily transferable to the Liouville function. So for the purpose of these talks, these are multiplicative functions of equivalent difficulty if you are interested in statistical properties. So now the Liouville function is equal to -1 if you have an odd number of prime factors counting multiplicity +1 otherwise. Its values are supposed to be randomly distributed. These are the first few values. So based on this, several conjectures have been formulated. The one that I will focus today is the Chowla conjecture, so which asserts that all these correlations are 0, at least for distinct values of sheaves. Equivalently, or perhaps it's easier to think it if you want this way, it asserts that you will find on the range of lambda an equal number of -1s and +1s, or an equal number of minus, plus, plus, minus, plus, plus. There is no reason for this to give preference on any of these 4 configurations. And more generally, if you have a string of length L, it's supposed to occur equally frequently. So with natural density, since you have 2 to the L of them, 1 over 2 to the L. Okay, so this is a reasonable expectation. And this asymptotic that I wrote here, it's an easy exercise to see that it's exactly equivalent with what I said over here. Okay, so what is known? So the case L is equal to 1 is known to be elementarily equivalent to the prime number theorem. So this is known. Okay? The average of the Liouville function are 0, or equivalently, you find 1 and minus 1 equally frequently. All the other cases, at least in the form that it's stated here, are open, at least till now. But if you now do the following thing, if you allow me to relax a little bit the averaging scheme and work with logarithmic averages, which in terms of several applications that one has in mind is equally good. For example, let's say that you want to prove that all possible patterns of plus minus ones appear on the edge of lambda, okay? Consecutive plus minus ones. So I don't have to work with Cesaro average. I could just go and choose an averaging scheme that I like and prove this asymptotic. Then I would get something about logarithmic density, which is equally good. So if you relax it to logarithmic average, that was a breakthrough of tau in 2015, and later another interesting result of tau and Caravine in 2018. So they verified the logarithmically average variant of the Chowla conjecture for L is equal to 2. That was the result in 2015. And then for all odd values of L, this is the joint result with Caravine. Okay. Be careful though that if you verify this, let's say for 2021, it doesn't mean that you get it for 2020. It doesn't go like that. Okay. The even L's are the tough one. Okay. And it doesn't give you, if you verify this for all L, it doesn't give you anything about sign patterns of length, let's say 4 or 3. If you want to say something about sign patterns of length L, you need to verify the conjecture for all values less than or equal to L. Okay. Okay, so this is what is known, and up to now, even in this logarithmic form, the problem remains open. So the first open case now is L is equal to 4. Okay. What I would like to do is talk about some variants of this of the logarithmically average Chowla conjecture that we can reformulate in ergodic terms and prove them using ergodic theory in an essential way. Let me also mention that at least one of the two proofs that Tau and Teravainen gave for this odd Chowla, as we say, uses ergodic theory. It's an interesting ergodic argument in an essential way. There is another one that is more elementary. And another note, let me say this now, that most of the things I would say apply to more general multiplicative functions. The same for the odd, but you have to put some necessary conditions there. And I will focus on the Liouville function, okay? Good. So let me tell you a couple of things that I chose to show you how we can prove them. I have avoided statements regarding, let's say, the Sarnak conjecture, because the statements are, even to understand the statement, you require some ergodic theory, and the proofs are more intricate in their use of ergodic theory. So I will present you two statements that I believe are also interesting and require less amount of knowledge in ergodic theory. For example, this one. So this is something you can understand. Let's say you take this weighted Chowla averages with weights given by irrational, this linear exponential sequences, but with alpha irrational. It's very important that alpha is irrational. You expect the same thing to hold for alpha rational, but there is no rational value for which this can prove or so on. So this is a joint result with Bernard Host. So the case L is equal to 1 is a very well-known result of all the result of Debussy and Delange, proved actually even for Cesaro averages. Even for L is equal to, I believe this is non-trivial. I do not know of a way to prove it. Let's say I cannot modify easily whatever tau did for L is equal to for the unweighted version to get this one. Okay. And for us, in order to prove such a statement is all or nothing statement. You either prove it for all L or you cannot prove it for anything. Okay? This is how the proof method proceeds. So the weight there can be replaced with more general things like phases that use polynomials, but you have to require at least one non-constant coefficient to be irrational, okay, some irrationality gain, or even more general weights that admit an ergodic formulation, total ergodic and zero entropy and zero mean. Never mind, this statement is interesting enough. And also lambda could be replaced with marginal bounded multiplicative functions, or you could have L different bounded multiplicative functions. Similar result holds with a bit more effort. Okay, so the main interest in this proof is actually that it is proved using ergodic theory in an essential way. I will show you how we construct some measure preserved systems associated with, let's say, the Liouville function here. And in order to prove something like that, an equivalent statement would be to show that this system has no irrational spectrum, no irrational eigenvalue. I will be more precise in a bit, okay? So let me mention also the second statement I would like to prove, and then I will tell you how we construct the systems, and then briefly tell you how we prove what we want to prove. Okay, so of course, if you want to stop me and ask any questions, I will be happy to answer. So the second statement, so let me take one moment to reformulate the Chowla, the logarithmic Chowla conjecture in a convenient form to make an analogy with the statement I want to prove. So I will say that I have L sequences. We say that they are essentially distinct. If you take any pair of them, they're different for large enough values of L. Okay? They could agree in the first few values, but they will be different after some point. So it can be shown that the Chowla conjecture in its logarithmic form is equivalent with the seemingly simpler statement that if you have essentially distinct sequences, then the average of these, if you take the limit also after encodes within is zero. Of course, if you have Chowla, you immediately get this and you don't need any limit. Okay? The point is, even if you have this limiting formulation, you can go back to Chowla. I will not tell you how, but it's, believe me, it's true. So what we will do is, I will not verify this case. I will verify this in the case where these are not only different, but they are in some sense independent. I will now tell you what independent means. So we will say that L sequences are independent. If you take any non-trivial integer combination of these, you get something that is non-zero for large values of N. For example, if I give you some polynomials that are rationally dependent, n squared or n to the third, then these are definitely independent. If I take any integer combination of n squared n to the third, it's a cubic, so it could have at least 3 solutions. Okay, but you could take also very sparse sequences, 2 to the n, 3 to the n, 4 to the n. You give me any L sequences that have different growth rate. It could be 2 to the 2 to the n or whatever you want. They will be dependent for obvious reasons. Okay, just take the limit. Okay, so all these sequences qualify for my statement. But they could also be linear. Okay, but not linear with rational coefficients. These can not be independent. But with irrational coefficients, let's say n squared root 2, n squared root 3, it's an easy exercise to show that such sequences are independent. Okay? But I cannot use n comma 2n or n to the n to the n plus n. These sequences are not independent. I can find integer combinations, the obvious ones that give me 0 for every n. Okay? So, of course, the statement, no surprise, we can show that, since I defined this terminology, that the Chowla conjecture holds along independent sequences in this form. Okay? So we'll see how we do this. And as a corollary, if you want, if you're interested in these things, I guess this is a combinatoric seminar, so here is an application with combinatoric flavor about patterns that you can find in the range of lambda. If you give me independent sequences, any kind of combination of plus or minus 1, arbitrary one, then this will be attained along some independent shift. This is what it says. Okay, you choose which shift, you choose the sequences, and then all these patterns will be found. We have to be careful with the quantifiers that for all large enough n, not only there exists an n, for all large enough n, there is some n. This can be shifted so that you will attain the same pattern. And more, you can say that actually the logarithmic descent of the n's for which this is attained is the correct one to converge to the correct one. Okay, so these are the two statements I will show, but now I will back up and tell you some general process. I give you any sequence. Perhaps you're interested in the digits of pi or square root of 2. Okay, this is a sequence of now finite valued sequence. Any sequence you give me, you are interested to study statistical properties. The method that I will tell you will work to get a starting point, but whether you can proceed and make an interesting statements is a big question. We can't for multiplicative functions for reasons that I will tell you. So I will construct now a system given, you give me any bounded sequence, I will construct a measure preserved system that models its statistical properties. So this is probably the most important slide in terms of notation. So if you don't understand something, please ask me, because this corresponds I will use all the time. So first of all, the setup is in ergodic theory is a simple one. So you have a finite measure space, and we typically take it to have a measure 1. That's why we call it probability space. And then we have a transformation from x to x. Okay, this is a transformation of the space, not from x to r. These are functions. This is a transformation that preserves the measure. Okay. If it's invertible, you can look on the forward image. You say if it's not, then you look on the inverse image. So any set, the inverse image could be totally a different set, but it will have the same measure. Okay, you can think of rotations on the circle if you want, or the dumpling map, or some unipotent transformation of the torus. I will mention some examples later. These are the structural examples, or the Bernoulli shifts that I will mention later. These are the random examples. So any such triple, we call it a measure preserved system. Okay. So these are the things that we want to construct. And ergodic theory is the study of properties of measure preserving systems. It's a very abstract setup. Okay, so here is this correspondence principle of Furstenberg that he initially used it in order to prove Samaredis theorem. He applied it for indicator functions of sets, or for sets if you want. We need a slight variant that applies to sequence, but it's exactly the same principle with the same proof. Okay, so you give me an arbitrary sequence, let's say from n to the, this u denotes the complex unit disk. Okay, it's a bounded sequence, very important. Now, if it's not defined on the negative integers, you put it 0. That's fine. The only thing that matters is what happens in natural numbers. Forget about the subsequential thing. I will mention why we use this later on. The important thing is the following one, is that we can construct a system. It's an explicit one, but you don't have to know how we construct it. It's not something complicated. But the property that I mentioned here is what you have to remember. We can construct a system and a function so that the statistics of the function equal the statistics of the sequence. Or I guess the other way. We have the statistics of the sequence, and we want to find the system and the function that represents the statistics. Okay, so you give me a sequence, I will find the system and the function. It will be fixed so that this identity holds for all L and for all shifts of N1 and L. Okay, it's not that I change the shifts, I will find a different system or function. It will be universal. Okay, now because the right hand side here may first of all, I use logarithmic average. I could use any average scheme I like, but later on I need logarithmic average. That's why I use logarithmic averages here. And why I say for every sequence I go to a subsequence, perhaps this average do not exist. I definitely do not want to impose assumptions that correlation limits exist, because this could be extremely hard to verify. For Chowla, it could be as hard, probably as hard as verifying Chowla. So that's why we formulate in this sense. For every sequence, you can find the subsequence, this diagonal argument, so that all these limits exist because you have countable many choices. Hence, you can always assume without loss of generality that these limits exist. Then you construct the system. Okay. So the thing I want you to remember is this identity, okay, that I will use all the time. I have a sequence, there is a system and the function. Correlations of the star function are equal to correlations of the system. Okay, any such system, we call it Furstenberg system of the sequence. And note that if you give me a sequence, because I may have the limits may not exist. I may have uncountably many Furstenberg systems associated with this. I don't care. I all call them Furstenberg systems of A. This will play no role for our argument. If you want for simplicity to assume the limits exist, it's fine. It doesn't cause any trouble for my arguments, but we don't have. Okay? So, and when alpha is the Liouville function, because we will focus on the Liouville function from now on, we call it a Liouville system, okay? But important for the, this principle apply to any bounded sequence that you would like to study. So what the first few steps that I will mention are the same always. What you do afterwards is the question. And in case you wonder how you construct this thing, although I will only use the identity, not so much the construction, the space that we use X is the sequence space, V to the Z, okay, because the range is V, the space of sequence with a range U. I said V before anyway. T is always the shift. So if you have a sequence, you shift it by 1 point. And the function is always the evaluation of the zero coordinate. So all these things are always fixed. So the only thing that varies, because something has to vary, is the measure. So it's basically a correspondence between sequences and measures on the sequence space with a shift transformation. And the measure, in a sense, is uniquely determined by the correlation conditions that you have. So you don't have to think a lot. The properties that you want to have uniquely determine the measure. If you also put complex conjugate here and here, then this is a true statement. Okay, so and if you wanted an explicit distribution for the measure, but we will not use this in this form, is this Weikstad limit of this Dirac method, evaluated on the shifts of A. You think of A as a point on the sequence space. But it is the identity that I want you to remember. So if you have any question on this slide, please stop me now. I'll be happy to answer. Okay. So, so what we're going to do with this correspondence principle, first I will show you some examples. This is what we're going to do. So, if I have a sequence, a very useful thing to do is, I mean, it would be optimal if we could determine the structure, the precise structure of its Furstenberg system. What I mean by this is fuzzy, but determine the structure means if you can prove it's completely random, prove it. If you can prove it's completely structured, whatever this means, prove it. If you can prove it's isomorphic, as we say in Ergodic with some very simple system, prove it. So let's start with the simplest possible sequences. So e to the n alpha. When I write this is the usual notation, e to the 2 pi n alpha. Okay. So with alpha, rational, irrational, I don't care. So it's easy to verify. So you have this Furstenberg system, which is a shift on the sequence space with some measure, but it should be no surprise that this system is isomorphic with one that is very simple, and it's actually a rotation on the circle. And if you want a function that has the same statistics as this sequence defined on the circle, is this f of x is equal to e to the n. This is no surprise because if you take iterates of t, when I say t to the n, I forgot to say, I mean t, you compose it with t n times. Then what you will get here is x plus n alpha. So you had an alpha, you have an alpha here, so it's no surprise that this is the system that really models, the measure preserving system that models this sequence. Now, if you go to e to the n squared alpha, a similar thing holds, but you have to think a little bit more what is the appropriate system. You want, optimally, you could contract the system so that you take iterates and you see these guys. Then this is a good hint that the Furstenberg system of this sequence will be isomorphic with this system. So in this case, if you consider this, it's an affine transformation on this two-dimensional torus. You take f of xy e to the y. Then it's a computation that whatever correlations you get for t to the n, you will get for this sequence also. So the Furstenberg system of this sequence is isomorphic with this very structured one. Again, there is no surprise, because if you take iterate c to the n of xy, you will see n square hangings on the second coordinate. So this is why this works out. But sometimes things work out in a more in a stranger way. For example, let's take this sequence, e to the n to the 3/2, or any alpha that is let's say not an integer. Then it's not I cannot think of a system of algebraic nature, so, like the previous one, that if I take n iterates, I will the n to the 3/2 will pop out. It just doesn't happen like that. But this doesn't mean that you cannot be isomorphic with something of this form, because what I want is not a point-wise identity. I want the statistics to be the same. So this is a little bit more surprising, but it's a true fact that the the Furstenberg system of this sequence is isomorphic again to a system of algebraic nature. Exactly this one with this function. So it's a computation, not very difficult one, that if you take iterates of this function, the statistics, you will get exactly the same statistics as this sequence. Now, the fact that I have a power between 1 and 2 is the reason that I put two coordinates here. If I had a power that is between 2020 2021, I would put here 2021 coordinates and some unipotent. There is an explicit for this, okay? And notice that if I take nth powers of this, I will not see n to the 3/2, I will just see x, y plus n x. Nevertheless, they have the same statistics. So sometimes you may have to think a bit to see what is really going on. So, and if these are all structured systems, how about a random one? If you take a random sequence of plus minus 1, then almost surely this is a consequence of the law of large numbers. The Furstenberg system that you will get is what we call a Bernoulli system. These are the most random systems, coin flips in ergodic theory. Basically, you have a measure on the sequence space, which is the product measure. Okay. When we say Bernoulli system, is the most random systems, the most randoms you could possibly have. Okay, so these are some examples. Now, let's go back to our multiplicative function, which is the Liouville function. Of course, we expect to be very random, so it's a very natural to expect that the Furstenberg systems of the Liouville function are Bernoulli systems, okay, because they're supposed to be random. And so it's easily shown to be equivalent. This fact is easily shown to be equivalent to the logarithmic Chowla conjecture, okay? So there is no obvious advantage in working in this direction. You just reformulated the hard problem into another hard one, okay? Now, the important thing in ergodic theory is that perhaps you have some tools. There are several conditions that allow you to check Bernoulli by verifying simpler properties. None of this has produced any fruits, but also it gives you terminology that you don't have when you work in the integers. Perhaps you try and go improve randomness properties that are more accessible. The weakest one is ergodicity, but even this one, no invariant set means ergodic. Even this one is very hard to verify. And actually, interestingly, at some point, I proved that if you have ergodicity, which is the weakest form of randomness, you will get Bernoulli for the Liouville function or for a larger class of multiplicative function. But so ergodicity looks, again, very hard. And another reformulation given by Tau that I will use later on, I will go very briefly through it. If you don't know what the semi-norm is, I will not tell you now. So the logarithmic Chowla conjecture is equivalent to the fact that for every Furstenberg system, this function f, when I say f now, I mean this function f of x that is x0, this specific function f that we construct in the correspondence principle has Garfos-Kara semi-norms equal to 0. It's Garfos-Kara uniform, as we say, okay? These are some semi-norms that are defined by some formulas. motivated by the analogous manner of sin combinatorics. So what is known about this conjecture? So if you have going from the left to the right is not hard. From the right to the left is much more difficult. But this is something proven by the equivalence. And this is actually a way to go about this conjecture. So for k is equal to 1, it's known. This is a result that was another breakthrough of Mathematical. It's pretty much equivalent to the fact that the Liouville function on the typical short interval has average whatever this equation tells you. For k is equal to 2 is an open problem, an important open problem. This is the higher order uniformity of the Liouville local uniformity. This is a Fourier uniformity conjecture, as I said. There has been some progress, but it has not been verified. Basically, you want to exclude the scenario that the Liouville function on a sequence of interval, the increase to infinity looks like a linear exponential phase, but the phase is allowed to change on every interval. This is much harder because there are multiplicative functions, complex values that arise this way. Okay. Okay, so I will use later on actually a variant of a boost of this Mathematical result where I put rational twists here, but I don't soup. I just have a rational. That was a boost given by Mathematical. Okay, so let's go now and see what is the starting point in all these problems when you try to give an ergodic reformulation. You need some feedback from number theory to get started. Okay, so the feedback that we always use at the start in all the applications, I mentioned the two and also the result about the All Chowla, the ergodic proof, is some identity that Tau proved in order to prove this binary Chowla, Logarithmic Chowla, in its simplest form, but this is not the form I need. It tells you that if you get a sequence and you average it out, and then you average over dilates, prime dilates, important, then you will get the same average. This is a strange property. I wouldn't say that it's I would say it's a bit unexpected. You see it for the first time. It's caused by the fact that this multiplication by p is kind of independent operations. So it's important that we use logarithmic average. Everything is important here. If you use 0, it's false. And it's important that you average over primes, or let's say some relatively prime set of integers that have some good property. Okay, so this property, I'm sorry. So this one is easy to prove using the Bernoulli inequality. The one that I will use is not easy and was proved by Tau using this entropy decrement argument. So what it tells you is an enhancement of this. Look on the right-hand side. This is correlations of A with dilated and average out. And on the left-hand side is the same expression, but the difference is that instead of n, I have Pn. So somehow I can make this P vanish exactly as I made it here. Okay? So Tau proved this, and it's very useful. Let's see why. Let's go and apply this identity for lambda, for the Liouville function. Then the important thing is that for multiplicative functions, lambda p n plus nj factors to lambda p times lambda n plus nj. And then you have L terms, so you will have a -1 to the L that I put on the right-hand side. So you get this interesting identity. The important thing now is that you have an identity where both in the left and the right-hand side, you have correlations. It's n plus something, n plus something. If I left it like that, this identity is not transferable to ergodic theorem because although the right-hand side is fine, it's n plus something, the left-hand side is not, it's pn plus something. This is no good. This is the reason why multiplicativity helps a lot. If you give me digits of pi, I cannot tell you anything about the pn plus pi. And so I have nothing useful to get started. So for the first result that I mentioned, the weighted Chowla with irrational weights, I only need this ingredient. I don't need anything else. For the second one, I will also use this mathematical. Okay? So let's go and see. Okay, I have 15 minutes. Let me go quickly. Let me just tell you how we reformulate the statements, very briefly how the argument goes. So if you use this correspondence principle of Furstenberg, and you use also this tau. First of all, the tau, the identity of tau, written in ergodic terms, I'm sorry, I should mention this first, gives you exactly this thing, using the correspondence. Okay? That you have any Liouville system, if you use as f of x this specific function, then the correlations of this function are equal to this average correlation of a prime dilate, and you have this -1. So what we do later on is just study properties of systems that have this very curious property and try to extract as many properties as we can. Okay? So from this point on, you forget the Liouville function. You may only remember later on that you have mathematical irrational also. You just remember this identity. So let's go and see now how we prove this thing, a very rough sketch, this weighted Chowla with irrational weights. So the first transfer, which is an elementary exercise, is that it suffices to show, in order to prove the statement, it suffices to show that every Liouville system does not have irrational spectrum, which means if you you cannot have a non-trivial eigenfunction with irrational eigenvalue. If you have such an identity with an irrational, then G is necessary. Okay. How you get from if you have this, why you have this. If you go and square or use van der Corput, then you arrive at some correlation identity. If you transfer it using Furstenberg correspondence, from it, and you assume that something is non-zero, from it you will read a non-trivial e to the 2 pi I a eigenfunction. It's a simple exercise, okay? So to go from here to here, so the point is how we prove this statement. So now we have a purely ergodic statement to prove, and our start, I just repeat the statement here. Very briefly, I will tell you the steps. You don't have to understand them completely, just to get a sense of what is going on. So our starting point is we have a system that satisfies this identity of tau, and we want to show that any such system cannot have an irrational eigenfunction. Okay, that's the goal. So the first property that we prove, this is actually the most important property, and I'm cheating here because I don't give you the details. It's not an easy one to prove, but it follows from this identity and various other ergodic identities that had been proven in the past. So it takes some effort, is that these Furstenberg systems that you have are not only translation invariant, but they're also kind of dilation invariant. This is an outcome of multiplicativity, meaning that if you consider these maps, tau r of x, that sends x of j to xrj, then this is a measure preserving, at least for r's in some arithmetic progression. Let's assume for all r, okay? It will not make a difference. But the truth is that the system can be approximated actually by systems that have this property. This is closer to a true statement, okay? Why is this useful? Let's say that we have an e to the alpha eigenfunction, we want to show that it's zero. Then these tau r maps that preserve the measure mu, this is the outcome of multiplicativity, because of the commutation relation T tau r is equal to tau r T to the r. It's a simple exercise to see that TRG will be an e to the alpha over r eigenfunction, modulo r roots of unity. Now this is a strange thing because e to the alpha r for alpha irrational is going to change. So this will produce mutually orthogonal functions. This starts to become a little bit strange for irrational values. So let's say if we want to show that G is zero, suffice to show that it's orthogonal to all products of iterates of this function f. F is this specific function. This is a very, very simple thing to check. So I will show you how we sketch how we show this for L is equal to 2. L is equal to 1 is easier. The 2 is the interesting case. A similar argument also in general. So suppose that I want to show that G is orthogonal to F times TR. Then I will apply this T to the R, and which is measure preserving, and T to the R F is equal to F. And use the commutational relation and average of all eligible R that are R's on some arithmetic progression. I will get this identity. A very, very simple thing. Then, if I use van der Corput, it suffices to show, it's a simple computation, that this new expression, is zero. Now, the important thing is that before I had T to the R, depends on R, but now I have a fixed function. So let's go and look on this one, which varies with that. So S is fixed. I want to show that this is 0 for every S fixed, and I average over R. So this T to the R of this is going to be a computation, as I mentioned, because of 3, and E to the minus F over R plus S alpha eigenfunction. And these, as R varies, are different eigenfunctions because alpha is irrational, hence mutually orthogonal, hence they should converge weakly to 0, hence you will have this actually with limit. This is how it goes. So it's an operator theoretic argument. Okay, I cheated in 2. Ergodic theory is used there too also, but this is the main idea. But notice also that the way we will proceed is by considering an infinitary object, which is an eigenfunction, and excluding its existence. It's not easy to translate this into a more traditional number theoretic statement. Perhaps there is a way, I don't know. I guess there is always a way. Okay, so let me move very quickly to the second statement also. I will give you a brief summary. This Chowla alone independent sequence. Starting point is again the same. We will use Gauss identity, first time correspondence, and it suffices to prove a property about general measure preserving system. Here I need the additional feedback, otherwise the proper right is not true. That this function f that comes from first time correspondence is orthogonal to all the rational eigenfunctions. We call it the rational Kronecker, and this is outcome of this Radziwill with a boost of tau. Okay, so we get this as a starting point, additional feedback here. I didn't use it before. So suffice to show that for arbitrary measure preserving system, we have a function with this property. Then you have this strange ergodic theorem. Okay, of course, this ergodic theorem had not been studied before because we had no reason to study them, but now they become relevant, and we can use very well developed machinery to prove them. Very briefly, let me tell you how we do this. So this is the statement. I write this here for several functions. It's easier to prove it in this form. And I assume one of them is orthogonal to the rational. I will prove that this is 0. So we go through a series of steps. First of all, we don't particularly like the fact that we have a few primes, but using Gauss uniformity of the modified von Michael function, you can replace this average by an average by this is easy to say because we have the result. Okay, the result is very hard to prove, but we can use it now and reduce to, and so we can think of having this as an average over 10, okay, for practical purpose. Now, a second reduction is we use the Hoskera theory of characteristic factors. Again, another hard result to prove, but we have it. This will tell you that it suffices to verify the statement for a particular class of systems of algebraic nature that we call nil systems. These are generalizations of rotations of the circle or compact abelian group rotation. Okay, so just to get a sense of this, if you want, try it as an exercise. It's really an exercise. If you are the simplest possible nil system, let's say irrational rotation on the torus with the assumption I gave you, verify this identity. So essentially what you have to prove is what I write here. And if you plug in complex exponential, then you can approximate fj is equal to e to the kjx. You see that what you really need in order for this property to be valid is this independent property that I mentioned before. So this the independence assumption comes exactly because I want this thing to be true for irrational rotation. This is what this condition gives, the least acute. Okay, and then magically it works for all nil systems. I will not tell you how, but using equidistribution techniques in nil manifolds, several standard things, and you have to think also a little bit. You get this properly also. Okay. There is an article on the archive if you want to see details. It's not very complicated. Okay, so this is how we prove also this thing. Starting point the same as before. Now identity. What we do next is okay. So let me also close with a couple of open problems that are kind of intriguing. So for sure, the first one. We proved with Bernard that Liouville systems cannot have irrational eigenfunctions, and this is a general property of multiplicative functions, bounded multiplicative functions. But for Liouville, the Liouville function, or a more general class of multiplicative functions, let's say that take plus or minus 1 and are periodic, as I say, you would expect that they also have no rational value. Prove this. This is not of equivalent difficulty as Chowla. Okay, in ergodic terms, proving that you don't have an eigenfunction is supposed to be much easier than showing that you're not Bernoulli. But I have no idea how to prove this. I've tried and failed. So some interesting consequence of this, of course, the obvious one would be you would get weighted Chowla with these weights where A is a rational non-integer. For example, you can put minus here. And another curious one, this would answer a conjecture that, on the range of the Liouville function, before you verify Chowla, you try to verify other various things about the pattern. One of the famous unsolved problems that you can find an arbitrary number of consecutive ones or minus ones on the range of lambda. Okay, up to now, I don't know, I don't remember, perhaps 5 or something like that. Okay, infinitely often. So, yeah, this would follow from this statement. It's not hard to see. It would follow from this statement plus Semerelli's theorem. That's why I need plus. I could not produce plus minus lambda. I will get the plus and the minus, okay, from this. But we don't know how to verify this. So a problem. Not even for, let's say, alpha. Okay, for minus. The fact that minus 1 is not an eigenvalue for lambda is not known. Be careful, the Mobius function does have rational eigenvalue. Okay. It takes the value 0. And another curious variant of the Chowla conjecture, I don't think that anybody has tried this, it arose on the work that I mentioned before, is the following one. This is Chowla with, instead of translating, you dilate. But of course, you cannot dilate with integers because the statement I write would be false. So I dilate with irrationals, basically. So but what I want, the property I want is that pairwise to have irrational quotients. Let's say take square root of 2, square root of 3, square root of 5. Okay. Then prove this logarithmic average variant of Chowla for these things. And we'll prove anything other than L is equal to 1. I can do L is equal to 1, but anybody else can do also, so it's not very interesting. And for L is odd, like the odd Chowla, you would not need any assumption. It should be true for all AIs that are positive, I guess. Okay. But it's not known for L is equal to 2 or 3. There is no obvious way to translate it in ergodic theory for similar problems that have n, just one alpha and sheaves of n's. I could translate them in ergodic theory. But now that I have difference, I didn't manage to write an equivalent ergodic statement. Would be very happy to see, perhaps I mean something obvious I missed, I don't know. Okay. Or prove it any way you like for L is equal to 2, or if it's more convenient for you, for all odd L or whatever. Not clear at all. So I will leave you with